here we are with number 3 for the FRQs. So this one is also 12 points, just like number 2, and we've got rotational motion happening here. So number 3 states that the left end of a rod of length D and rotational inertia I is attached to a frictionless horizontal surface by a frictionless pivot, as shown above. Point C marks the center or the midpoint of the rod. The rod is initially motionless, but is free to rotate around the pivot. A student will slide a disk of mass m sub disk toward the rod with a velocity v0 perpendicular to the rod, and the disk will stick to the rod a distance x from the pivot. The student wants the rod disk system to end up with as much angular speed as possible. So letter A says that suppose the rod is much more massive than the disk. To give the rod as much angular speed as possible, should the student make the disk hit the rod to the left of point C, at point C, or to the right of point C? So, first of all, to get a good conceptual understanding of what this question is asking us, basically it's asking us what is going to make this rod move the fastest, okay? So, if I've got my rod here, okay, and here's my midpoint, or my center, here's the pivot. So kind of intuitively, you know, right, if you know how doors work, if you want the door to move as quickly as possible, you know that you have to apply your torque to the end of the door right here. So our answer for letter A is going to be that we want to apply our torque to the right of the midpoint. And it wants us to explain our answer. So, of course, utilizing an equation to prove your answer is always a good thing. So we know that the torque is going to be equal to R times sine theta times the force. Okay, this whole thing is 1 since theta is equal to 90 degrees. So our justification in this equation is that the farther away from the pivot the greater the torque if the force remains constant. And we're going to assume constant force here because the problem didn't tell us any differently, okay? If it does, of course, keep that in mind, but here we can assume that the force is constant, so the only variable that's going to be affecting the torque that you have applied here is going to be the R, or the distance from the pivot. So we know we want to apply our force as far away from the pivot as possible. Okay, let's move on to part B. Part B says that on the internet, a student finds the following equation for the post-collision angular speed omega of the rod in this situation. Omega is equal to m disk x v0 all over I. Regardless of whether this equation for angular speed is correct, does it agree with your qualitative reasoning in part A? In other words, does this equation for omega have the expected dependence as reasoned in part A? Okay. So exactly like they said, don't worry about if the equation itself is correct or not, okay? That's not what we're worried about here. All we're doing here is exploring the dependency of the variables upon one another. So you always know that whatever is on the right side of your equation is an independent variable, and then your left side of your equation is your dependent variable. So we know that angular speed is going to depend on all the other stuff on the right side. We just need to figure out if that's going to be a direct dependence, like direct proportionality, or if it's going to be inverse proportionality, meaning as one goes up, the other one goes down. So let's go back over here and let's go ahead and write that equation. So for part B, we know that omega is equal to mass of the disk x v0 all over I, okay? And the correct answer to this one is going to be that yes, the equation represents the expected dependence. And here's why. We have the mass of the disk, we have our position, and we have our initial velocity. All of these are directly variable, directly proportional to omega. So we would expect that if these go up, that means that angular speed also goes up, which is true. So my justification for that we expect direct proportionality between mass and initial velocity with angular and this equation exhibits that. You know, since the values are in the numerator of the equation. Okay? So again, don't worry about what the actual variables are, okay? Take a variable, and if it's directly proportional, you know that, yes, this is what we expect, right? Like you expect angular velocity, or your angular speed, to increase if you increase the mass of the disk. Higher mass means it goes further whenever it makes boom contact with the rod. Same thing with position. Farther away you are from the pivot point, the more angular speed you will impart upon the rod, and the faster you're going initially, the more angular speed you're going to impart upon the rod. So that's our justification and our answer for part B. Now let's go ahead and go on to part C. Pause the video here if you need to get anything. And we see that another student deriving an equation for the post-collision angular speed omega of the rod makes a mistake and comes up with omega is equal to I x v naught over m disk d to the fourth power. Without deriving the correct equation, how can you tell that this equation is not plausible? In other words, that it does not make physical sense. Briefly explain your reasoning. So our reasoning is going to be along the same lines as it was for letter B, okay? So we know that, and it already kind of gives us a hint, right, that it's not actually going to make sense, so we don't need to try and justify it making sense. So for part C, whoopsie. Equation does not make sense. It shows an inverse relationship between, if we go and look at the equation over here, we see that the mass of the disk is in the denominator and omega is, of course, our dependent variable. So we have an inverse relationship between mass and angular speed here. And kind of intuitively speaking, that doesn't make sense. You would expect that if you collide, if the rod collides with something that has more mass, then it's going to move faster after it experiences that collision. It's the difference between being hit by a bike and being hit by a truck. Whenever you get hit by the vehicle, you're going to fly farther whenever you get hit by the truck versus being hit by the bike. So, so one would expect a higher mass on the rod. cool. That's letter C. Pause the video here if you need it. And we will go on to the last part. Last two parts anyway. So for parts D and E, do not assume that the rod is much more massive than the disk. So immediately before colliding with the rod, the disk's rotational inertia about the pivot is m disk x squared, and its angular momentum with respect to the pivot is m disk v naught x. Derive an equation for the post-collision angular speed omega of the rod. Express your answer in the terms of D, m disk, I, x, v naught, and physical constants as appropriate. Fine. All right. So here what we're going to use is we're going to use our knowledge of angular momentum. And this is something that I didn't get to cover a whole lot in class. So make sure that you go back and review angular momentum. So just like our equation for linear momentum, where linear momentum was P is equal to m times v, we're just going to turn these variables into our angular motion variables. So the angular velocity variable is capital L. Our angular mass is I, and our angular speed is omega. So we know that we want omega by itself. So what we're going to do is we're going to, of course, try and get omega by itself. But we also understand that we have an initial angular momentum has to be equal to the final angular momentum. So it tells us that to begin with, the angular momentum of the disk itself, right, is all that we have, right, because the rod is not moving. So now, on the right side, we're going to have the angular momentum of, the angular momentum of the disk and the angular momentum of the rod. So here we go. We know that the angular momentum of the disk was given to us, and it's given as m disk times x squared v naught. Okay. And here, what we're going to want to do is we're going to want to plug in our variables that we know. Okay. So we know that this whole thing is going to be equal to I omega. And our I now is going to be equal to the I for the disk plus the I for the rod, all multiplied by omega. So what we're going to do after that point is we're going to plug in the variables that we know. We already have this, so I'm just going to rewrite it. And it told us that the I of the disk was m of the disk x squared plus the rotational inertia of the rod multiplied by omega. Now all you have to do to go ahead and get that by itself is divide both sides by m disk x squared plus the I of the rod. Same thing over here. Oopsie, made a boo-boo there. And you end up with the angular velocity is equal to m disk x squared v naught plus I of the rod. And you can actually leave your answer just like this. It is perfectly valid to leave your answer like this instead of reducing further. If you were to reduce further, you would end up with I plus m disk x squared as your final answer. But this is perfectly fine. The AP exam will accept this as your answer. So last part now, pause the video here if you need to get anything. Okay. Letter E, consider the collision for which your equation in part D was derived, except now suppose the disk bounces backward off the rod instead of sticking to the rod. Is the post-collision angular speed of the rod when the disk bounces off of it greater than, less than, or equal to the post-collision angular speed of the rod when the disk sticks to it? So if we think about it this way, right, we know that our momentum on both sides has to equal, they have to equal each other, right? Whoopsie. Life is pain. Okay. So we're going to need to figure out what each of these are, both when we have an inelastic collision and when we have an elastic collision. So for the inelastic, which is what we have to begin with, we would have the L of the disk is equal to, we know that it's going to be I going to be that, like we figured out earlier. And for an elastic one, it's the same thing. But now we have so we have two separate angular velocities here. And what we're going to need to do is we're going to need to evaluate how exactly the angular speed changes in each of these scenarios. Here, the angular speed of the disk, it goes from some positive number, right, to another positive number, but it is also less positive as before. And we go to 0 to the less positive, right, because they are moving together. And for here, our disk goes from positive to negative because now the disk is moving backwards because it bounced off of the rod. And so we need to figure out what the rod goes to, right? So we're worried about the magnitude change here, okay? And the magnitude change is greater when it comes to this scenario. So if the change is greater here with the elastic collision, in order to compensate, to actually balance out and to obey the conservation of momentum, we're going to have to make this rod more positive. So we have the greater angular speed here. It's kind of like if you're on a number line and you go from positive 3 to negative 6, well, then the rod would have to go from 0 to 9 to balance that magnitude change out. Meanwhile, on the right side, you could go from positive 3 to positive 1. Well, then the rod would only have to go from 0 to positive 2 in order for that to balance out, okay? So yes, we have a greater change in momentum here with the elastic collision, so we have a greater change in the speed of the rod with the elastic equation. That's it. FRQ done. It's a lot, so make sure you go back and review any concepts that you had difficulty with for this problem. Adios.